Welcome to this module on analytical skills. Now, presently I'm recording it for my grade 12s who are doing this right at the end of their further studies in physics course, and they will be writing the final exam in October. But this recording will also be used for those learners who are going to do it in either toward the end of year one or the beginning of year two in the new way that we are going to structure further studies in physics at Parklands College. So analytical skills is basically the scientific method. And if one looks at the subtopics that we're going to look at, we're going to be looking at SI units, uncertainties and significant figures, and graph analysis. So there'll be 3 separate lessons on each of these. Today I'm going to do SI units, and in doing that, we are going to focus on the following. Recall the following base quantities in their units, namely mass, length, time, current, temperature, amount of substance, and luminous intensity. We're going to express derived units in terms of the SI base units, and then we're going to use SI base units to check the homogeneity of physical equations. So without further ado, let's look at the SI base units. So the SI system, SI stands for Système International. A little bit of history is that there was, at one time, we had the metric system and the imperial system, and we still have remnants of them around. In the United Kingdom and in the US, imperial units like pounds and inches, PSI, pounds per square inch, are still used. And then there was the metric system, which was the French system, where, for instance, the meter is a unit from the metric system. That was kilograms, which was what under the metric system. So now the scientific community in the world realized that there was a bit of a problem. So they came together and they set up a standard international system, which is used in science. So when we look at the SI system, we can see that on the outside we have the kilogram, which is for mass. We have the meter, which is for distance. We have the second, which is for time. We have the ampere, which is for electrical current. We have the Kelvin, which is for temperature, what we also call absolute temperature. We've come across that before for the grade 12s when we did thermodynamics. We have the mole, which is the unit that we use in chemistry for amount of substance, linked to Avogadro's number. Then we have candela, which is to do with light intensity. So these units, here they are what we call the base unit. So we've got kilogram, meter, seconds, ampere, Kelvin, mole, candela. Right. Now, if we, for instance, these are the base units. So if we now look at something like distance, which is, we look at velocity or speed, which is distance over time. Velocity is changing position over time. And we're going to land up with length over time, which will be meters per second. So if we are working with, for instance, temperature, then we normally work in degrees Celsius in South Africa. We have to do a conversion to Kelvin. In chemistry, we work with the mole. We don't really work with it in the physics course here. We haven't worked with candela at all, and we're not going to, not in this course. When it comes to current, it's interesting with current. So if you take, for instance, charge is I times T, current times time. So current times time, ampere seconds, is going to give us the coulomb, which is the unit for charge that we use. So the SI base units are basically used in the context of science throughout the world. However, we do find the remnants of the imperial system in many countries. Here in South Africa, we don't really work with pounds anymore when it comes to pressure. Americans like to work with PSI, pounds per square inch, but we, having been a British colony, we used to use it, but in the 20th and the 21st century, we moved away to working with the SI system, which, in my opinion, is better. So when we talk about derived units, then these are the ones that are derived from the 7 base units. So, for instance, newtons, joules, pascals, these are, for instance, pascals is newtons per square meter. Joules is Newton meters. Newtons is kilograms meters per second squared. We'll come back to this at a later stage. So to deduce the base units, it is necessary to use the definition of the quantity. So for instance, if we look at force, if we look at Newton's second law, force is mass times acceleration. And so Newton is kilograms meters per second squared. See, force is newtons, it's a derived unit. And we have so I just want to quickly put this top on here, don't want to lose it. So mass is in kilograms, as we know. But acceleration, if we take a look at acceleration, okay, acceleration is the change in velocity over the change in time. And I just want to stay in this recording. And so if we look at the change in velocity, this is the change in position versus the change in time. So change in position has got the unit of distance, which is meter. The change in time is the unit of time, which is seconds. So for velocity, we're actually working in meters per second, or meters times second to the minus 1, which means now that when we come to acceleration, we are working with meters per second to the minus 1 over second. When we bring that upstairs, we are working with meters per second to the meters per second squared, or meters times second to the minus 2. So it should be meters per second squared. Right, so we can see how by using the equation of the quantity, we can actually get what it is equivalent to in base units. So the Newton is therefore equal to kilograms meters per second squared. The joule is the unit of energy, and there's different ways of deriving the joule, but you can use, for instance, this formula, EK equals a half mv squared, which is kinetic energy. But you can also use it, as I will show you, you can use other energy equations or formulae to do that. So yeah, you can see that energy, which is in joule, so that would be, this would be joule. This would be joule. It's going to be half, hasn't got a unit. Mass is kilograms. Velocity is meters per second squared. So it's meters squared second to the minus 1 to the power 2 second to the minus 2. That's kilograms meters squared second to the minus 2. So therefore, 1 joule is, in base units, is kilograms meters per second, meters squared second to the minus 2. But let me show you how we could do this using the definition of work. So if we take work, we know that work is the transfer of energy from the agent to the object, but we also know that it is the force in question times the change in position caused by that force times the cos theta of the angle, cos of the angle between the change in position vector and the force vector. Let me bring that down. So in the NSC syllabus, we work with the work done by a force to change the energy of an object, is equal to the force, the magnitude of the force applied, times delta x, which is the change in position, the effective change in position, times cos theta. Now, if we say that, okay, we know that work is energy, transfer of energy, forces in newtons, okay, and distance is in meters. Now, newtons is a derived unit, right? So we know that newtons comes from force equals mass times acceleration. So therefore, the newton, as we've just shown, is kilograms meters second to the minus 2. So the joule is going to be kilograms meters times second to the minus 2 times the unit for mass is kilograms. Sorry, my bad. Sorry, I apologize. That M is not mass, that M is a unit, so it's meters. It should be meters. Apologies for that. M there doesn't stand for mass, it stands for the base unit for change in position, which is M. So therefore, joules is equivalent to kilograms. Meter times meter is meters squared, second to the minus 2. And so we get the same result even though we used a different equation. Right, so now the Pascal, we do pressure in grade 8 at our school. So pressure is force over area. We know that pressure is force over area. Force we know is in newtons, right? So pressure in Pascal, newtons per square meter, but we've already shown that newtons is kilograms meters times second to the minus 2. Now if you divide by meters squared, you're going to times by meters to the minus 2. So kilogram second to the minus 2 meter to the 1 times meter to the minus 2 is going to give you meter to the minus 1. So therefore the Pascal is in base units of kilograms meters to the minus 1 second to the minus 2. Right, so derived units we've just worked with there. We can see that these are, this is newtons, this is joules, and this is pascals. So testing the homogeneity, it's not such an easy word to pronounce. We can say homogeneous or homogeneous. So homogeneity, that's how I pronounce it, implies checking the units on both sides of an equation to determine if they are equal, if the units are actually equal. So we're checking to see whether the equation is actually correct. We're using, call it unit analysis. In order, we're using units to test whether the equation has the correct structure. So examples, test the homogeneity of the following equations or formulae. Right, so now this is going to be the exercise that I would like you to do. I would like you to pause and I would like you to try them. You might find that some of them are not easy, okay? And these are formulae that you as a grade 12 student at this stage should have come into contact with, depending upon if you're, let's say, for instance, a grade 9 or a grade 10 at Parklands College, you're doing the AP physics and you come across this, further studies in physics, my apology, then you'll find that you might not have come across this yet. This is the velocity equation. This is the final velocity equals the initial velocity of an object plus the acceleration of the object times the time interval that the object is accelerating. This is what's known as the impulse momentum equation. This is the net force that's being applied to an object. This is the interval, time interval over which that net force is being applied, equal to the mass of the object times the change in the velocity of the object due to the net force acting over that time interval. We call this the change in momentum. This is also from the grade 12 syllabus, the work done by the non-conservative forces is equal to the changing potential energy and the changing kinetic energy of the object, or sorry, not of the object, of the system. Okay. Q equals I delta T. I think all of you, irrespective of where you are, should have already encountered this, because we do this in grade 9 at Parklands College. I equals Q over T. It's the definition of electrical current. Electrical current is equal to the amount of charge flowing past a point in a conductor per unit time. Q equals MC delta T comes from the AP physics course, further studies in physics course, and that is for heat transfer. So Q here and Q here are different. This Q is in the context of electricity. This Q is charge. This Q is in the context of thermodynamics. This Q is heat energy. So this, the unit for this is joules. The unit for that is coulombs. So this I'm going to leave you with, and I will then post the solutions to this a day or two after this lesson has been posted, so that it gives you some time to work on this. I do think this might take you some time to do. Thank you very much. In the next lesson, we will go and we'll be looking at uncertainties and significant figures, and this is very relevant to experimentation, being able to identify the types of errors and uncertainties and calculating them. So I thank you for viewing this, and I hope it has been enlightening and useful, and until the next time, goodbye.